Ever stop to wonder how the totally chaotic alternating current surging out of your wall outlet is magically tamed into the smooth, steady direct current that your smartphone or laptop absolutely demands? I mean, it's a massive electrical plumbing problem, and solving it requires some seriously clever engineering. Welcome to this explainer. Today, we're going to unpack exactly how that transformation happens, step by step.
So here's the core issue. We've got a total mismatch in our electrical ecosystem. Your wall socket pumps out AC, or alternating current, which constantly reverses direction 50 times a second. But the sensitive electronic circuits inside your favorite gadgets, they need DC, or direct current, a steady, one-way flow of electricity. To bridge that gap, we rely on a brilliant little component called the crystal diode. Think of a diode as a highly effective, one-way check valve for electrical flow. It lets the electrical current flow through in one direction, but immediately slams shut if it tries to flow backward.
All right, here's our roadmap for this explainer. We'll be covering 1. The AC to DC problem. 2. Halfway rectifiers explained. 3. Full wave and center tap. 4. The bridge rectifier upgrade. 5. Output quality and ripple. And finally, 6. Troubleshooting and comparison.
Let's start with section 1, the AC to DC problem.
You see, the reason this problem even exists comes down to pure economics. For power companies, generating and transmitting AC power over long distances is incredibly cost-effective. That's why the power grid uses 50 Hz sinusoidal AC. But for things like the microchips in our devices, an AC supply is virtually useless. A DC supply is strictly required to function. When that steady DC is needed, the mains AC supply is rectified using crystal diodes. Basically, a rectifier is just a circuit that takes that wavy 50 Hz AC and forces it into a strict one-way street.
Moving right along to section 2, half-wave rectifiers explained.
Take a look at this circuit setup. We generally feed our AC supply through a transformer first. This is absolutely crucial because it lets us step the voltage down to whatever our gadget actually needs, and it safely isolates our rectifier circuit from the main power line, keeping us safe from dangerous shocks. Following the transformer, we have a single crystal diode sitting in series with our load. Notice the resulting graph. That single diode is bluntly chopping off the entire negative downward half of the incoming AC wave.
Let's break down exactly how it pulls that off. Think of it like a rhythmic gate. During the positive half cycle of the AC input, the diode becomes forward biased. The gate opens up, and current successfully flows through the load in one direction. But during the negative half cycle, the diode becomes reverse biased, and the gate slams shut. No current is conducted, meaning zero voltage appears across the load. Because it only lets that positive half through, the output frequency matches the input frequency exactly at 50 Hz, but the power is just completely blocked half the time.
And that leads us to this pretty dismal number, 40.6%. That is the absolute maximum efficiency of a half-wave rectifier. Since the AC supply is only delivering power half the time, most of your AC power simply isn't converting to DC. Plus, the output is highly pulsating, which means you'd need elaborate filtering to smooth it out. We can definitely do better than this. Which brings us to section 3, full wave and center tap.
Since throwing away half our power is a terrible design, we need 2 diodes working alternately to capture the whole wave. Look closely at this clever schematic. By splitting the transformer's secondary winding right down the middle with a center tap, we essentially create 2 separate voltage pathways. During the positive half cycle, the top diode is forward biased and conducts current through the load. During the negative half cycle, that top diode turns off, but the bottom diode becomes forward biased and starts conducting. The brilliant part is, whether it's the top or bottom diode doing the work, they both push the current through the load in the exact same direction.
This completely illustrates the upgrade we just made. Because we're no longer wasting the negative half of the cycle, we've just doubled our maximum rectifier efficiency to an impressive 81.2%. And even better, because we're getting 2 pulses of power for every single cycle of AC input, our output frequency has doubled compared to the input. If 50 Hz goes in, 100 Hz comes out. Having that higher output frequency actually makes smoothing and filtering the power way easier down the line.
But as any engineer will tell you, every solution brings its own set of new problems. First, physically locating and manufacturing that center tap perfectly on the transformer winding is notoriously difficult. Second, our DC output voltage is relatively low because each diode is only ever utilizing half of the transformer's total secondary voltage at any one time. Finally, and this is the big one, the resting diode gets slammed with double the maximum voltage, a peak inverse voltage or PIV of 2 Vm. If you want your circuit to survive that kind of electrical pressure without burning out, you're forced to buy expensive, highly rated diodes.
All right, Section 4, the bridge rectifier upgrade. To fix those issues, we arrive at the absolute hero of our explainer, the full-wave bridge rectifier. This design is honestly pure genius. By arranging 4 diodes in this diamond-shaped bridge configuration, we completely eliminate the need for a bulky, hard-to-make center-tap transformer. Here's the flow. During the positive wave, a diagonally opposite pair of diodes becomes forward-biased, acting as a series path pushing current to the right. During the negative wave, that pair switches off and the other diagonal pair takes over, still pushing the current to the right through the load. Both halves of the AC wave are captured perfectly.
Sure, it requires 4 diodes instead of 2, but it's a massive win overall. Because 2 diodes are conducting in series at any given time across the full transformer winding, the output voltage is twice that of a center tap circuit for the exact same transformer. But you want to know the biggest cost saver? The peak inverse voltage pressure on each reverse bias diode drops in half, back down to just VM. This means you can use standard, far cheaper parts to achieve a highly efficient full-wave output.
Moving to Section 5, Output Quality and Ripple.
Now that we have this highly efficient circuit, we need to honestly assess the quality of the DC we're creating. While our output is flowing in only one direction, notice how heavily pulsating it is. It certainly doesn't look like the perfectly flat line of a battery. Mathematically, a pulsating wave like this is actually 2 things combined. It's hiding a true, perfectly flat DC component, but there is an unwanted wavy AC fluctuation superimposed right on top of it.
We actually measure this annoyance using a metric called the ripple factor. The AC component is completely undesirable. It's what causes those visual pulsations. So the overall effectiveness of your rectifier depends directly on the magnitude of this AC component in your output. We find it by dividing the root mean square value of the AC component by the value of the DC component. Put simply, the smaller this ripple factor number is, the better and more stable your rectifier is at doing its job.
Finally, Section 6, Troubleshooting in Comparison. Let's step into the real world for a second to see what happens when things break. Faults usually fall into 2 camps, transformer faults and diode faults. See that protective fuse sitting on the primary side of the transformer? If a transformer winding completely shorts out, or if one of the diodes fully shorts and starts acting like a simple piece of wire, an excessive amount of current will violently flow through the circuit. That surge will immediately cause this primary fuse to blow, safely cutting the power and saving your expensive equipment from a total meltdown. But here is a really surprising fact. Not all faults will actually blow that fuse. Some are silent killers called open circuits. If a winding completely breaks, your output voltage just drops to 0. Easy enough to find with a resistance check. But if a single diode opens in a full wave setup, meaning it just completely stops letting any current through, the primary fuse will not blow. Instead, your expensive, highly efficient full wave bridge just secretly downgrades itself. Because it's suddenly missing half its team, the output will silently transform into a terrible, pulsating half-wave rectifier. The only fix is to test and replace the bad diode.
This table right here perfectly summarizes our whole journey today. The half wave is out, it's way too inefficient at 40.6% and has a terrible ripple factor of 1.21. The center tap fixes the efficiency and brings the ripple down to a solid 0.48, but it forces us to use expensive diodes that can handle a massive 2 VM peak inverse voltage. Therefore, the bridge rectifier is our clear, undisputed champion. When costs and performance are on the line, engineers invariably reach for the bridge circuit. It brilliantly pairs the high 81.2% efficiency and low 0.48 ripple of a full wave with the cheap, low voltage requirements of a half wave. It's just the best overall performer, hands down.
So, we've successfully forced our chaotic AC wall power into a highly efficient, one-way street of DC. But it is still pulsating. Those sensitive electronics in your laptop definitely wouldn't be happy with that power just yet. So how do we completely iron out that remaining 0.48 ripple factor into the pure, flat, battery-like power that our modern lives depend on? Well, that is a story for our next explainer, where we'll introduce the absolute magic of filter circuits. Until then, keep questioning how your world works.